Okay, so section 2.1 is angles in standard position. So when we're looking at this, the key ideas here are there are main kind of angles that we look at that we use as a reference point when we're solving other angles for either triangles or just angles in general. So we're going to come back to the key ideas at the end, and you can fill that in once we're done all of the examples. So angles in standard position. An angle that is drawn in standard position must have its vertex at the origin of the Cartesian plane, and its initial arm must coincide with the positive x-axis. So for whatever reason on here, my y-axis did not show up, but that should be there. So for an angle to be in standard position, and I know this is a little bit blurry on here, but it should be all right in your notes. The starting side of it, or the initial arm, is always on the positive x-axis. So that's what this says here. This is the initial arm. The terminal arm then is the final position after you've rotated your angles to get it to whatever measurement you want. So for this particular example, this side here in quadrant 2 is our terminal arm. The angle is always labeled theta, so that's that Greek letter with the the O with the line through it. The vertex of the angle must always be at an origin of the Cartesian coordinate plane, and the positive angles are measured in a counterclockwise direction. So the example is here. So for this example, this angle would be considered to be in standard position because the initial arm starts at x. It is our angle rotation goes to the terminal arm, which is there. Our vertex of the angle is also at the origin. So that's kind of the key parts for an angle to be in standard position. So our 4 quadrants of the Cartesian plane, we label starting at the top right and then moving around in a counterclockwise direction. Cartesian coordinate planes are always labeled with Roman numerals, and if you're identifying it, like if a question said what quadrant is 72 degrees in, then you would say it's in quadrant 1. So that's the way you would identify that. So we're going to draw each of these angles in standard position and identify the quadrant in which it lies. So what you would do is you would use your protractor and you would put it on your vertex. And this always takes a little bit of a challenge to make this shrink for me. Doesn't want to shrink. Okay, so anyway, you put it on your vertex. You measure your 60 degrees, so starting from 0. So 0 is here, 60 degrees ends up there. So if I move my... So 60 degrees, if I matched up my line here, would be something like that. What I need to indicate is this is my angle direction, so it means it's a positive 60, and this would be in quadrant 1. I'm just going to see if I can squish this in. Sometimes it'll let it make it smaller, but nope. Okay. So the second angle is supposed to be in 300 degrees. So I know to go from my 0 point here to find 300 degrees. So if you can see in the middle of my circle there, so I'm up to 180 degrees to there. Well, that doesn't give me enough, so that means I need to give this a spin. Oops, I have to put down my paper. So where'd my... Oh, gave me a full one. That's even better. Never done that before. So 300 degrees then, if I'm starting at here at 0, I should spin this, if it'll let me. There we go. Where's 0? There's 0. There's this on my... So there's 0, 300 degrees. If I look around, goes over into quadrant 4 right there. So give this a spin. You can see my numbers are changing. There's 290, so there's 300 right there. So 300 degrees is into quadrant 4. There we go. Oh, takes me a while to remember what to do. So quadrant, or 300 degrees was approximately right there. So this is in quadrant 4. So that's C. B should be 100 degrees. So we'll do B here. 100 degrees then, knowing that this is 90. If I take and line that up. So 90 degrees is, I have to bring, whoops. Get that out of the way. Oh, that's nice. Oh, okay. 90 degrees is up here. So then 100 degrees is just going to be 10 past it, so it'll be there. So 100 degrees is about right there. Pretend that's at the vertex. Okay. So 100 degrees then would be in quadrant 2. This should be quadrant 1. So reference angles then. It says for each angle in standard position, there is a corresponding acute angle called the reference angle, which is the acute angle between the terminal arm and the nearest x-axis. So the difference between an angle in standard position and a reference angle is that it doesn't matter which x-axis it is. For standard position, you have to have the positive x-axis. For a reference angle, it's either positive or negative x-axis. So it says thus, any reference angle is between 0 and 90 degrees. So it has to be acute, and it has to be then, because it's acute, it has to be less than 90 degrees, or between 0 and 90. So an angle in quadrant 1, if this is my angle theta, whoops, that shouldn't be a Q, it should be a theta. My reference angle then would be just that angle. So my reference angle would be the same, it would be, they would equal each other. So in quadrant 1, your angle is the same as your reference angle. In quadrant 2, so if this was my angle here, this is my angle theta, my reference angle then is from the nearest x-axis to the terminal arm, so this would be my reference angle. So in quadrant 2, my reference angle is going to be 180 degrees, so whatever, because I'm going from the negative x-axis here, so it's going to be 180 degrees minus whatever the angle was will give you your reference angle. So that's in quadrant 2. So quadrant 3 then, if this is my angle going to here, so this is my theta, your reference angle then is going to be the distance from your terminal arm to that nearest x-axis. So that is your reference angle there. So your reference angle then is going to be, to calculate that, you'd use 180 minus, I want to make sure I put that the right way. Sorry, it should be the other way. Whoops. It's your angle, theta, minus 180 degrees will give you your reference angle. Quadrant 4 then. So my angle could be something like that. So that means it's gone all the way. Whoop, I started that a little. It's starting from here and going around to there. So that's theta. So my reference angle again is between the terminal arm and the nearest x-axis. So that's my theta r. So then my reference angle is going to be 360 degrees minus theta will give you the reference angle. Okay. So the next part here says, draw each angle in standard position and find the reference angle. So 30 degrees is approximately right there. So that's my theta. In quadrant 1, this is in quadrant 1, so that means that my reference angle is just equal to my angle. So the reference angle here is equal to 30 degrees. 250 degrees, so that's going to be 180 and then another, oops, that should be, I believe, 180 plus that 270. So it's going to be in quadrant 3. So quadrant 3, in order to find my angle, if theta is equal to 250, to find my reference angle then, so this is my reference angle here, my reference angle then is going to be my, right here, it was your angle, which that should be a 250 minus 180, so the reference angle is 70 degrees. 325 is going to end up, oh, my alignment is way off here, somewhere over there. So this is my angle here that I'm doing. I did it again. I started at the angle instead of at the x-axis. So it goes to there. So that's my theta. So my reference angle is from the terminal arm to the x-axis. So that would mean for this one, my reference angle is going to be 360 degrees because it's in quadrant 4 minus theta. So that's going to be 35 degrees. D is 100 degrees. So 100 degrees is just past the 90. So there's theta. So that ends up being in quadrant 2. And in quadrant 2, to find that, I have to take 180 degrees minus theta to get my reference angle. So that's going to be 80 degrees. So what I'm looking for is this measurement here. Reference angles are going to come in to play in the next section when we're calculating all the positive value, or all the values for possible values, not positive, possible values for different trig functions. So it says determine the angle in standard position when an angle of 60 degrees is reflected. So if I'm starting with an angle at 60 degrees, so 60 degrees is approximately right there. So that's my angle. if I'm reflecting it in the y, then that means it's going to be, and I'll erase this in a second, but it's going to be reflected on this side. So it's just like you took a mirror, set the mirror on the y-axis, and see what your reflection will get you. So a reflection of this means that, and I'll just do a dotted line, so it's going to look like that. So this angle then, because it's asking me for the angle in standard position of that reflected angle, so it's going to go from here to here. So if I take a look at this, I've gone 60 degrees. If I go up to the y-axis, that's going to be, this distance here is 30 degrees. So then that means the reflected part here is also 30 degrees from that y-axis. So that means that the measurement of the reflected angle will be 120 degrees. So it's reflected in the x-axis, so then that means it's flipped down. So I'm starting here. This is my angle. A reflection in the x-axis means that it's going to be reflecting down this way. Oops, so that means it's going to look like that. So now the angle that I'm measuring, these two would be the same. So if this was 60 degrees here, then this dotted part is 60 degrees. The angle in standard position then means that I'm starting from here and I'm going to that arm. So that means that I've gone my 180, my 270 to here, and then this measurement here. Well, I know to go from here to here is 60, so to go from, I'm just going to change my color there. From here to here was 60, so from here to here means that to go from this distance to this distance, I would have to go on another 30. So there's two ways to find this. I can say, okay, I know I've gone 270 degrees around, plus another 30, which would be 300 degrees. Or I can think of this as being my reference angle, so it's in quadrant 3. If my reference angle was 60 degrees, then that means the rest of it has to be 360 minus 60. So I'm just working backwards. So either way would work. So if I start with an angle of, in standard position, whoops, that is 60 degrees. So that's that measurement there. It's reflected in the y-axis, so then that means it's going to be reflected like that. And then it's reflected in the x-axis, so then it's flipped down. That's looking more like 45 degrees then. Oh boy. Sorry, this is... Okay, so then that means my total angle here to be in standard position, that's what I'm looking for. So I know I've gone from here to here. From here to here will give me 90 degrees. Then I have another 90 degrees, and then I've got this reflection part here. So if this part here, I know that this is 60 degrees on this side, so then that means my reflection part on this side has to be 60 degrees as well. So my angle is going to be 180 plus that 60, so it's 240 degrees. The other way to look at it is, okay, I know from my x-axis on this side, or sorry, my y-axis, this would have to be 30 degrees here. So then I know I'm working with 270 degrees minus 30, which also gives me that 240 degrees. So there's different ways of solving it. Or I could have added it. I could have went 90, 90, 60. Same thing. Okay, special right triangles. You're going to come across these a couple of times in math, and it's good to memorize the ratios for these. So our first special right triangle is the 45, 45, 90 triangle. So what we're looking at is a unit triangle. So what we say is we've taken a triangle with legs that have units of 1, and if the legs are all 1s, then that means, remember, the legs are the sides that aren't the hypotenuse of a right triangle. So if this has legs of 1, then that means that my hypotenuse is going to be c squared equals a squared plus b squared. So 1 squared plus 1 squared is 2. Square root of 2 is square root 2. So the sides opposite the 45 are 1, and the side opposite the hypotenuse is square root 2. So that would mean that sine of 45 degrees, so if sine is opposite over hypotenuse, it's going to be 1 over square root 2. And if you remember from our chapter on radicals, you could rationalize the denominator on this, so it would be 1 over square root 2 times square root 2 over square root 2. So this is actually square root 2 over 2. So sometimes in your textbook they're going to rationalize the denominator, so your answer will be square root 2 over 2. And sometimes they'll just leave it as an improper radical like that. So cosine. So 45 is what we're working at on the 45. Cosine is adjacent over hypotenuse, so that's 1 over square root 2, which is equal to square root 2 over 2. Tangent is just opposite over adjacent, so it's 1 over 1. So tangent to 45 is just equal to 1. So it says the trigonometric ratios on this page are given as exact values in fraction or radical form as opposed to an approximate decimal. So if you're ever answering any questions and it says to find the measurements of your triangle in exact values, then you leave it as square root 2 over 2, you don't turn it into a decimal. So our other special triangle is the 30, 60, 90 triangle. So for the 30, 60, 90 triangle, this basically is, if you think of it as being an isosceles triangle with units of 2. So all of your legs are 2. So it's what they've done so that if it's, sorry, not an isosceles, an equilateral triangle. In an equilateral triangle, that means that all of your angles are 60 degrees. If we were to cut this in half, we would have this triangle here that's laying on its side. So we would have something that looked like this because we want a right triangle. So this would be cut in half, so it would be a 1. This side here would be a 2. And then you have to calculate the length of this leg here. This angle is 60 degrees. The top angle, because it's been cut in half, is 30 degrees. So that's where the 30, 60, 90 comes from. So to calculate the length of this side here, I'll call this side B, I would have to do c squared equals a squared plus b squared. So that's 2 squared is equal to 1 squared plus b squared. So I have 4 is equal to 1 plus b squared. 4 minus 1 is 3 is equal to b squared. Square root both sides. So square root 3 is equal to b. So that's where that value of square root 3 comes in. So the side opposite the 30 is always equal to 1. The side opposite the 60 is equal to square root 3, and the side opposite the right angle is equal to 2. If you're ever confused as to which the 1, 2 is square root 3, what goes with what side, you just need to remember that the smaller the angle, the smaller the measurement. So between 1 and square root 3, square root 3, if you work that into a decimal, it's 1 point something. So that means it's bigger than our side that's 1. Our hypotenuse, by definition, the hypotenuse has to be the longest side of a triangle, so that gets the biggest value. So if you're ever confused where the 2, 1, and square root 3 goes, you just have to remember what are the rules for the angles and sides in a triangle relationship. So the smallest angle always has the shortest side, the middle angle will have the middle measurement, and the hypotenuse always has the longest side. So sine of 30 then. Sine of 30, we're looking, this is our target angle of 30. Sine is opposite over hypotenuse, so that's going to be 1/2. Cos of 30, that's adjacent over hypotenuse, so that's square root 3 over 2. And tangent of 30 is opposite over adjacent, so that's 1 over square root 3, which is the same as square root 3 over 3, if I rationalize that denominator. So sine of 60, sine again is opposite over hypotenuse, so that's square root 3 over 2. Cos is adjacent over hypotenuse, so that's 1/2. And then tangent is opposite over adjacent, so that's square root 3 over 1, or just square root 3. Okay, so the next example says, suppose you have a standard angle of 60 degrees and the initial arm is 6.75 meters. What is the length of the terminal arm? So we're doing this on a Cartesian coordinate plane because we're talking about a standard position angle. But it doesn't matter that we're doing it on a Cartesian coordinate plane. We can finish off the last side and make a triangle out of this. So if the angle is in standard position, that means we're starting at, that's more of a 45 degree, but that's okay. So the angle is starting and it's ending here. We know that the initial arm, so the initial arm is always on the x-axis, so that's 6.75 meters. So we just drop down a dotted line, a perpendicular dotted line, as to approximately where we would say 6.75 meters is. So this question is asking what is the length of the terminal arm. So we want to know what is the length of this side here, which we'll call C because it's opposite the hypotenuse. So I know that this is 60 degrees. So if I take a look at this, I have my adjacent side, and I'm trying to find my hypotenuse. So adjacent and hypotenuse, based on my trig functions, is a cos. So I'm going to find cos of 60 degrees, and that's adjacent over hypotenuse. So cos of 60 degrees, adjacent is equal to 6.75. My hypotenuse is equal to C. So if I look back at my reference from my special triangles, cos of 60 degrees, and I'm not going to flip back there, but you can flip on your page, is equal to 1/2. So without having a scientific calculator, you can calculate this. So I know cos of 60 degrees is equal to 1/2. That means that 1/2 is equal to 6.75 over C. So by cross multiplying, I have C is equal to 2 times 6.75. So C is equal to 13.5. So the terminal arm would be 13.5 meters long. Okay, so you have your questions to work on based on the special right triangles and reference angles in standard position.